Hello, welcome to the first of hopefully more than one VFX video. Today's video is about the common shader techniques I've used for VFX. Most of these techniques can be translated to any engine, but the examples I'll be showing are implemented in Godot 4, so there will be some Godot specific pieces here and there. Without further ado, let's begin. Number 1. Tiling and offset. Tiling determines how many times our texture repeats, and offset determines how much our texture is displaced in UV coordinates. It's represented by this equation right here. We multiply our base UVs by our tiling first, and then we add the offset. This offset can be changed to indicate offset speed instead by multiplying it by time so that our texture is offset over time. Note that we can also change our texture's tiling behavior, having it set to repeat with repeat enable or to clamped with repeat disable. Repeat is what we've been seeing in the past examples, with the texture simply repeating when our UV goes past 1 on either axis. Clamp limits our texture to the 0 to 1 values, extending the edge pixels when values go out of bounds. Number 2. Masking. Masking is basically just multiplying our main texture with a grayscale texture to get a certain shape. To do this, we simply sample a grayscale texture and multiply that to our shader's alpha. Quick tip, you can use uv.r to get a horizontal gradient and uv.g to get a vertical gradient. You can also subtract these gradients from 1 to get the inverse. Number 3. Distortion. We take the definition from our trusty internet. According to Merriam-Webster, distortion is the act of twisting or altering something out of its original state. To achieve this in our shader, we sample another texture, usually a noise texture, and we add those values to our main texture's UV. We then multiply this with another value so we can control how distorted our texture will be. Number 4. Erosion. Erosion can also define how our effect fades beyond just manipulating our alpha. For this technique, we also use a grayscale texture. We sample this grayscale texture and apply a smooth step function. The smooth step's minimum is a value from 0 to 1, and the maximum is defined by an offset from the minimum. In this example, I define the smooth step's value based on a sine wave. With this technique, you'll find that the texture erodes from grayscale values 0 to 1 according to our texture. Number 5. Polar coordinates. Polar coordinates allow us to unwrap our textures radially. I linked a more in-depth explanation about polar coordinates in the description below. But as a quick summary, our usual Cartesian coordinate define points by their value in the x and y axes. Polar coordinates, on the other hand, define points by their angle and how far away it is. In Godot, that would look like this. We subtract our base UVs with 0.5, mapping our UVs from a 0 to 1 value to a negative 0.5 to 0.5 value. We then multiply that by 2 to map our UVs into a negative 1 to 1 value. Doing this will make our UV origin the center as opposed to the upper left. Our angle is calculated through an arctan for our uv.y and uv.x. This gives us a value from 0 to 2 pi or 0 to 360 degrees when converted. To simplify things for us, we divide this value by 2 pi. What's left to calculate is the distance, which we get through the length function. Our new polar UV is then a vector 2 of our angle and the distance. We can apply the same techniques from tiling and offset to manipulate our polar UVs. Number 6. Depth fade. Depth fade, or proximity fade, defines how our shader fades depending on how close it is with other geometry. Now, the easy way to get this formula is to set proximity fade in a standard 3D material first, and then converting it to a shader material. If you check the generated code, it includes the formula for depth fade. I don't completely understand how this is calculated, but I feel the need to explain what's happening somewhat, so I'll try to do it without making a total fool out of myself. So, to calculate for depth fade, you will need access to the depth texture, which can be accessed through the depth texture hint, called hint depth texture. Once you have this, you have to get the depth of the first opaque geometry pixel. We then compare this against the depth of our own particles pixel and smooth it out by our user-defined fade distance. Note that depth fade is merely a value from 0 to 1, and you can use it outside of manipulating the alpha. You can use it as an interpolator for color when your shader intersects with something, for example. And last, but definitely not least, we have number 7, particle lifetime. Particle lifetime is the lifetime of a particle, but normalized from 0 to 1. In Godot, this is available in the vertex stage of the shader, and we can access it through the Y value of the instance custom built-in. We can then pass this value to the fragment stage by making a varying variable. But the particle lifetime's full potential can be unlocked when used with curves. These curves will allow us to customize the behavior of all the techniques previously mentioned in the video. Curves are defined through sampler 2D variables and are sampled using the lifetime variable. Building on top of our erosion earlier, we can now plug in the particle lifetime as the minimum for our smooth step. We define our curve like so, and we'll see that our particle erodes towards the end depending on its lifetime. You can do a lot more using curves and the particle lifetime, so I encourage you to experiment with it. And that's it for this video. I hope this helped you out one way or another. If you have any questions or suggestions, please let me know in the comments below. Our project containing all the samples is available in my Patreon, which is linked in the description below as well. Thank you for watching, and I hope you have a great day.